Hey y'all, good morning, good afternoon, good middle of the night. Let's make sure to start, we get logged into Clever. All right, so how are we feeling today? Are we smiley? Are we frowny? Are we somewhere in the middle? How are we feeling? It's great to have you here for live lesson 12. We are finishing out week 6 with this lesson. Some reminders about a couple of things. So, this lesson is kind of filling out and finishing out our unit, talking about how the universe began. We're going to be thinking about the evidence that supports the Big Bang Theory, which we were introduced to last week. Some other reminders about just class in general. So, because this is the end of the 6 weeks, grades are going to be due here soon. So, please make sure that you're using any extra time you have to get caught up on assignments. All assignments are open free game for you guys to go back and make up. Make sure that you're checking comments, or if things are being returned that you thought were done but they weren't, see what's going on there, because I am looking at each and every one of your assignments, and if they're not up to the quality that I think they should be, I am returning them with the opportunity to make it better. Um, Remember that Edpuzzle needs to be, first of all, do your Edpuzzles. You don't just get to skip them, do them. Second of all, make sure that you are watching the video all the way through. If you're attending live lessons, it is important to remember our expectations, but I also hope that you are practicing these as safe, responsible, respectful, prepared, and here present students, even if you're at home and watching this in a recorded time on your own. If you ever come to the live lesson, remember our 2 mutes and a boot policy, as well as our way to use the team chat. And as always, thank you guys so much for your effort. Let's have a great lesson. So we are continuing to move through and talk about our first phenomena of the year, which is the very first phenomena, the Big Bang. And we're looking at this question: where does all matter and energy in the universe come from? Okay, the answer to that is going to be pointed back towards the Big Bang. Now, a bunch of y'all might be like, how do I know the Big Bang happened? What the heck is the Big Bang? Why do I care? Hopefully, at the end of the lesson, you will have a better understanding of what is going on. So let's recall last week, or last lesson, about the Big Bang. So think about the timeline and the Cosmos episode that we listened to. What do you remember about the Big Bang? Awesome. So the key things about the Big Bang are really can be broken down into 3 major points. The first is it occurred approximately 13.8 billion years ago. That's a typo. Billion years ago. All matter and energy originates from a single point. A singularity is what it is called. And since that Big Bang point and singularity, the universe has been expanding out ever since. So today's lesson is going to ask you to be working in our Big Bang Frere models. So what I need you to do is go to your classwork, open up number 28, Big Bang Evidence Frere models, and have this assignment open. All right, so what we're going to be doing is making some observations for the 3 Frere models. We're going to be looking at cosmic background radiation confetti, the composition of the universe comparison, and looking at what happens to the red shift of a balloon as you increase the volume of the balloon. So first of all, again, you should have this assignment open. You need to be on Cosmic Microwave Background, CMB, that Frere model. And we are just today going to be filling out the top left quadrants of the Frere models. The other 3 you guys are going to be responsible for afterwards as your assignment. So what you need to pay attention as we look at the next image and then video is, where's most of the confetti? How do you think that it might that this occurred, and where do you think that it all started from? All right, so take a look at this image, and you're going to add to your top left quadrant based on what you see there. Great. So what you might notice is that there's a bunch of confetti. We notice that it is spread out outside of even this grid, but it is highly concentrated in this area. That might suggest that the kind of origin point might be somewhere around here, and something caused it to explode out from this single point. So if you want to see what happened, here we go. I'm sorry it's grainy, and I'm sorry we sound crazy because we were doing this in slow-mo. But what happened on the previous slide is that there was an explosion in the form of a balloon popping. And the balloon, wherever the balloon was being held over, that is where the highest concentration was. But the force of the balloon popping caused the confetti to be spread out all over the place. All right. So you should have filled out this first quadrant with some observations and those thoughts about that. So what this is representing is what is called cosmic background radiation or cosmic microwave background. So what scientists see is this confetti. Well, I'm not really, but they see this radiation. They see this energy that is left over and has been stretched out over so much time and expansion to this microwave level. So this energy that is over time has been stretching until it's into the microwave and radio waves. So they're really, really big wavelengths. And it is in the background of pretty much every single image that is taken of the universe. So this, I'll explain in a little bit, provides evidence to support the Big Bang because this radiation can be like reverse engineered, taken back, okay, where they're using math and different things, and they can say that there was a single point where all of that matter and energy came from, and they can say that that energy that has expanded out is approximately 13.8 billion years old. So our next observation, you're going to move down the Freyer model, so to the second slide. And again, we are going to be looking at and working in the second, or the box here in the top left corner. The other three, again, you'll be doing on your own afterwards. So for Big Bang nucleosynthesis, all I need you to do is compare this orange expected amount of hydrogen and helium in the universe based on the Big Bang theory, and then compare it to what you see over here for the actual measured amounts of elements in the universe. What do you notice is similar? What do you notice is different? And what might that mean? Awesome. So if we think about the fact that right after the Big Bang, the first two elements that would have formed are hydrogen and helium. And the fact that those are the two elements that make up the majority of the universe, even though so much time has passed, that's really important in supporting the fact that the matter that was composed then is still the matter that has stuck around now. There's just been a little bit more time that allows for larger elements to be made through fusion inside of giant stars and supernovas. All right, our third piece of evidence, you're going to go down to the very last slide, which should say the expanding universe and redshift. Once again, we're doing the top left quadrant. So if we were doing this experiment in class, it's a pretty simple experiment, but what we would be doing is we would be modeling how our universe is expanding and what's that doing to wavelengths of different stars and galaxies as they move. So what we would do is we would blow up a balloon, we would put a wavelength. So remember from physics, a wavelength is from either peak to peak, trough to trough, or from the middle to the middle. But we're going to see what happens to the wavelength that you draw on a balloon as you increase the size of the balloon. So taking a look at this image here, which shows what would be happening, add to that top left quadrant what's going on. So what you see going on is as the balloon is expanding, the wavelength is getting longer, okay? And what is shown here, that wouldn't necessarily be shown because it wouldn't be changing colors, but actually the color of the wavelength, because of the wavelength, is shifting towards red. So what I mean by that is as a wavelength gets bigger, okay, as a wavelength gets bigger, so wavelengths are, again, peak to peak, or trough to trough, or middle to middle. As it gets bigger, it's moving more towards the red. So what we're seeing out in the universe is when we use telescopes to look at galaxies that are very far away from us, over time, they're shifting and their wavelengths are getting stretched out and longer and shifting red. If it was coming towards us, we would see them getting tighter and closer together, and that would be blue shifted. But what we're seeing is that they are getting red. And that is important because that tells us that the universe is still continually expanding. So our three major pillars that we talked about today are CMB, or cosmic background radiation, BBN, Big Bang nucleosynthesis, or the composition of hydrogen, helium in the universe, and then the red shifting of galaxies. And these three are super important and back up the Big Bang because of this. One, the cosmic background radiation shows that energy from the initial explosion has been left over and stretching throughout the universe and exists from that initial point. Okay, so it says that we have this initial explosion in energy. It has been expanding with the universe and exists throughout the universe. Okay, second, BBN shows that most of the universe is made up of the same two elements that would have been made right after the Big Bang. And thirdly, redshift shows us that distant stars and galaxies are shifting to red because the universe is continually getting bigger. This is our evidence in support of the Big Bang. So if we go back to those original points, the three things about the Big Bang, so it occurred 13.8 billion years ago. The cosmic microwave background supports that because that cosmic microwave background is 13.8 billion years ago, or is 13.8 billion years old. Okay, all matter and energy originates from a single point. The BBN also supports that. That supports the fact that all of those elements that would have been created at the single point are the same elements that we're seeing still existing throughout our universe now. And then the universe continually expanding, redshift is proving that because all of these galaxies that are far away from us continue to move away from us as time goes on because they have been redshifted. It's wild. It's crazy that this is something that happened so long ago in a place that is so unknown to us. And there's still many pieces of this process that don't make a whole lot of sense. But those three pieces of evidence provide a concrete support that the Big Bang created matter and energy in the universe. Our universe continues to expand, and it occurred 13.8 billion years ago. So, how are you feeling after this? So you have two assignments now assigned to you. You are going to finish filling out this Freyer model using the resources provided in the assignment. So there is additionally a reading, there is additionally a PowerPoint, as well as a video. Those three resources are there for you to finish filling out those three other boxes for each of the Freyer models. Okay, the second assignment is a Big Bang Quizlet. And that Quizlet, you will use the free learn option, and you're going to practice some of the vocabulary words that we have covered this unit because we're pretty much at the end now. And we want to start making sure that we've got everything and know all of these terms and ideas that we've been discussing. So to finish out your week, these are all of the assignments that you should have had for first, second, and third period. These you should have all of these for this week. For fifth and sixth and seventh period, these were the assignments that were assigned last week. These are the assignments that are assigned this week. That's all I have for you guys. Thank you so much for your time and effort, and I will see you on a live lesson again soon. Bye.